fundamental group. Marker. Let's see. So yeah, let me get a marker. See. Yeah, how you doing? Pretty good. Okay. So let's review some of the basics here. So if I have G and G prime as groups, um, and we'll just assume it's a multiplicative. So written multiplicatively. And then a homomorphism is f g to g prime is a noun such that f of xy is fx fy, and that'll be for all xy. And it automatically satisfies the equations f of e to e prime, so identity is identity, and inverse is the inverse. So this denotes identity G prime, element in the inverse in inverse in G prime. And the kernel of the homomorphism is the set, well, actually just kernel in general, not is a set of, it's basically the inverse image of the identity found in the range. And it is a subgroup of G. And then in a similar way, the image, if I take the image of G over, this is a subgroup of the codomain group here. So the homomorphism, just a little bit of jargon. Homomorphism F is called a monomorphism. Mono for one, if it's injective. And from Greek, an epimorphism. Epi is the preposition like on, upon. Yeah, it's like epidermis. If so, they went French for surjection. Yeah. And then Greek for epimorphism. If it is surjective. And of course, the highlight when you're in algebra is isomorphism. If it's a bijective. If it is bijective. And then just some on cosets is, suppose H is a subgroup of G, a group. And then we can let XH denote the left coset of all products H, or XH.
Scott?
Yeah.
So I think I should probably stop you here just before we continue on. So I don't know a whole lot about group theory, but just to verify, would those X and Y be like two different symmetries inside a particular group, and then you're basically applying one symmetry after the other?
Well, in permutations, yeah, you could think of the symmetry as an element. This is just generic though. So if I take any two elements that would have been in the first group G, then them interacting with each other inside of, think of it like happening like this. X and Y, they're in group G. They interact with their operation. Now I'm going to take the element that results from them interacting, and I'm going to then map that over with our homomorphism into some other. And that resulting element over here should be the same thing as if I took, let's see what happens if I map just X over into the other group. And what happens if I map just Y by itself over to the other group? Well, in order to preserve the algebraic property of the operation, then it should behave the same way. That a product here in G should basically result in equivalent product over in the new group. So even though they're different elements and they're represented differently because of this map F between them, their structure in the binary operation, and therefore, like the algebraic properties that you would think would come, those are all going to be the same. Yeah.
So is this multiplication always commutative?
Not necessarily. No, not necessarily. Yeah, groups are not required to commute. When the elements are, they are required to be associative. So, but it's not necessarily abelian. But abelian is an algebraic property. So if G is abelian, then G prime has to be, because otherwise this wouldn't always be true.
Oh,
Yeah. So
oh,
this is a structure, think of this as structure preserving, algebraic property preserving. So you can have different elements, different objects, but they'll still have the same, they'll behave the same way. Um,
okay.
And so then now what we're doing with a coset is I'm just taking a subset of a group that behaves still like a group, it doesn't act any different. And then I'm interacting elements inside of the group with that. And then that's going to generate its own set of sets, which are called cosets. So this is, yeah, so the set, what do I got here? Set XH is a left coset of H and G, and the collection of these cosets actually forms a partition. Forms a partition of the original group. And then we can do the same thing with right cosets. So similarly, we have right cosets, and then we just do it that way. And that's what we have to distinguish because we don't necessarily commute. So XH isn't required to be HX. Okay, and then this also forms a partition, and then we're going to call H normal a normal subgroup um, of G if we have that I can take X and H, and then X is inverse, and that is still an H. And then I need that to be true for points in the group and also elements in the subgroup. So the way that you form a quotient group here is essentially we're going to say, let's assume that we have XH if we have XH and HX. So if these cosets end up leading to the same exact partition, then we can have a quotient group, and we're going to have this operation XH coset here and a coset here gives you this new coset, and then this leads us to quotient. which we denote G divides H, or H divides G. And in the event that we don't actually have a quotient group as a notational thing, just for sake, this will conventionally be used for the right cosets. Okay. Cool. So let's move over to the topology side. It's actually a good review of my group theory to do these proofs in this section because new application.
Sure, any chance we could use these Rubik's cubes as examples for this?
Yeah, Rubik's cube is a group. It's a permutation group. Because every single time you make a rotation, you have permuted all of the elements. And if you can define the minimum number of permutations you can enact, that is, in speed cubing and WCA, we call it R, L, U, D, and then that is all you need. You can technically create more, and you can have R prime, L prime, U prime, D prime. But in reality, since it all cycles around on all four sides, R prime ends up just being R cubed and L. So really, this is the minimum number of permutations you need to describe every single permutation of 3 by 3 by 3.
Okay.
Yeah. So yes, that's how, I mean, algebra is how the algorithms were developed for cubing. Okay. That's its own thing. Take higher algebra with Dr. Lang. Okay, so we're gonna take a point in some sort of space, as we always do, and a path. I'm gonna take a path in X. Let's see, and then this begins and ends. And that's important. We need loops here. If we don't have loops, then your paths, if you try to do that operation where you append the paths to each other, well, you can't guarantee that you'll conveniently always start your next path where you left off. So we're going to just guarantee that that always happens by beginning and ending at the same point. And we call it a loop. It's called, very nice intuitive idea here, based at the point you chose. So the set of path homotopy classes of loops based at our anchor point with the operation path product is called the fundamental group of X relative to the base point X naught. It is denoted by P1 X naught. And as a general note, P1 X naught is also called the first homotopy group. And if there's a first, that implies there's an nth. So what we do is we say, okay, these do exist. So some Pn XX naught, but they actually exist for all of the positive integers. And that is hard math. A little too hard for today. So we'll just keep taking topology sections until we get through homotopy. Okay. But yes. So now I actually know what this is. Because I was like, oh, I'm not entirely sure the context for this. So there you go. It's related to these groups basically that you can create with spaces and points and loops and all the good things. So
wait, what is this a homotopy though?
homotopy. Think about this. Okay, I'm gonna here's an introductory example so that you have an idea of what on earth is happening. Okay, so suppose this is ping pong ball. Okay, so it's hollow. So we're only interested in we call this S. I wrote it out. We call this S2. And so suppose I choose some anchor point. So maybe I'll make the North Pole my anchor point. Now I'm going to think of all the loops I can have that are tracing on the surface of this globe kind of thing. So I could have a loop that kind of comes around and then ends up back there. And so I think to myself, how many different kinds of loops can I get here? So is this loop any different than, say, this loop? Well, not really, because if this is just on the surface, I can collapse this one and deform it through some homotopy onto that. So these paths, although they visually look different, they're homotopically equivalent to each other. So, and then we think, is it even possible to get a situation where I can even make a loop that's anchored here that's any different? Answer ends up being no. No matter how you do a closed loop, even if you went around the back side of it and went around, you could always essentially deform and find some sort of a path homotopy that will get your loop to deform and converge as just a single, the trivial loop, which is where you go nowhere. And so what happens is we'll say that the fundamental group here is the trivial group. Just one out. There's nothing to it. It is what it is. There's only one kind of path you can get. There's only one equivalence class you can get on this specific space S2.
So is that a zero? Is that supposed to be like a
This is convention. So if I were to be a little bit more technical, I would say a trivial group.
okay?
Yes. So this is the group of one element where that one element is its own identity and inverses.
Okay.
Now, if you put one hole in it, it's still the same. To make it different, you need to put two holes in it, I think.
Yes, because then you could probably loop around, make a figure eight, and then you couldn't pull all of them over. Yeah. Okay, so let me define. We will use this map in that proof here. It's a special kind of map we'll define. So that's alpha the path in my space X from X naught to X1. So we define a map by, see, we'll call it, for alpha, we'll call it alpha hat, which is going to be a map of the fundamental group to itself by the equation alpha hat of, if I take one of those homotopy equivalence classes, it should spit out the reverse of the path alpha product, so times then this path times alpha itself. Obviously, alpha is going to be well defined because we're basically just, what's happening is, here's my space X, and I have a path between, here's X naught, here's X1, and I'm saying, okay, well, here's a map. I want to go from alpha. So alpha is some sort of path. So from X naught to X1, we call that alpha. Reversing the direction is what putting the little bar is. So if I now go from X1 and reverse the direction, I'm going to call that alpha bar. And what I'm claiming is if I want to take some path, some other equivalence class, so any other path that would be homotopy equivalent to this, is that I'm essentially claiming I have formed, or wait, no, let's press that button today, because the F is related to the first one. It would actually have to be a loop on X naught. So it would be some sort of loop that's homotopic to that point, base point. Then what I'm saying is, okay, assign to every loop that is equivalent, homotopic equivalent to this through this map by starting at x1, going through the reverse, making my way around that, and then tracing back to x1. Because now I'm basically able to say, okay, does it make any difference if I start counting x naught versus x1? So if we're going to look at this example here, would it have mattered if I would have chosen a different anchor point? Does this somehow change? Doesn't. This is the fundamental group is unique to the basically what you have going on here. So this is a way to say, we're going to use this. I think we proved that they have to be. Yeah, I'm going to prove that this is an isomorphism, because to say that this is an isomorphism means that did I write the wrong point down? I wrote the wrong point. This is supposed to go to x1. Yeah, whoops. The fundamental group that'll come from this point will end up being the same getting from there. That's how I was gonna screw myself up. Okay. So yeah, let's prove that now. It's a pretty good exercise. So we're gonna prove that this map that we just defined, the map alpha hat is a group isomorphism. So which this will implicitly give significance to finding what these fundamental groups are, if they're unique. So we first simply we do a little bit of a computation here. If I take alpha hat, like I've defined it, and then I have my equivalence class here, and I make a product with alpha hat and then another called G, I'm going to first show that this is homomorphic. So what we're going to end up having is just alpha hat and being the same thing as if I had done the product of f and g inside. So by definition, by the way I defined this though, this is just going to be, by definition, alpha hat times f times alpha. And then this is by definition going to be alpha hat g alpha. And so that's going to go away because this is saying I want to go on this path like that and immediately go in the reverse direction. So it's the same as going from f to g here. So we have reverse alpha times f, going to alpha, reversing it so that undoes itself, and then g times alpha. But if you remember by definition, this sandwiching some sort of a path in between the reverse and that is how we defined alpha hat in the first place. So this is the alpha hat of f times g. So we see that there's a structure perfectly preserved.
That's the first time I've ever seen common sense applied to this class.
Yeah. So alpha hat is a homomorphism. And then we're going to show that it's an isomorphism. And what we're going to do is if B, or we need a new letter here, so let's do beta. If beta denotes the path, whoops, I meant to put a bar over that, that's the function. So alpha, so the reverse of alpha. Then we want beta hat to be basically the inverse of alpha hat. Because then if we have the inverse, the conditions for having an inverse are going to make it bijective, so it's isomorphic. And oh yeah, so we can compute for some element h. So we compute for all, or really for each equivalence class that is in the fundamental group for the one anchored at now x1 instead of x0. we have two things. First, b hat of h. By definition, that's going to be the reverse of beta times h times beta, which, by the way, we chose beta to note the reverse of a. So this is alpha times h times the reverse of alpha. And alpha hat of beta hat of h is going to be, first we have the alpha reverse of alpha, and then this is what we plugged in, which is this result right here. So I'll put that in parentheses. We have the alpha times h times reverse alpha, and then complete the definition, which you can probably see. If I reverse and then undo it, that's gone. And then if I go the reverse and undo it, it's gone. So all that's left is I'm essentially just doing the loop H. And so in the same way that so Victor, you know how it's like if you have two functions that are inverses of each other, that you'll have something like f of x, and then if g of x is the inverse of f of x, you would expect that f of g of x is equal to x.
Yeah.
That's basically what we're doing here. Is we're saying this is functioning as the x, beta has one of the maps, alpha has one of the maps, and because alpha hat of beta hat of some element gives you that element back. So the argument to go beta hat of alpha hat is identical. You just, instead of doing it this way, plug in and you'll compute the other side and you'll still get.
So you're assuming that, well, I don't know if it's an assumption or not, but you're assuming that going in one direction and going back to the same direction doesn't matter depending on what order you do.
Right, because I mean, so if I start here, and if I go here, so if I have to find this path to be alpha,
Yeah.
going from here to here, if I just start here and then retrace all of the steps, you'll end up back exactly where you were.
My only confusion is that how come you can't apply that level of common sense to most things here?
Because when we did the homotopies last week, we actually defined all of the hardware for the reverse.
Okay.
There is a rigorous, yes, there's stuff under the hood even for the reverse. It's
Okay.
just not worth repeating
I see.
today. Yeah.
Sorry, fair point.
So then a similar computation follows this. That's the way to say I figured out one way, which means that doing it the other way is not going to be anything new. It's just symbols. Okay.
So by symmetry.
By symmetry. Ooh. Is it symmetry? Is it analog? Is it some more arguments? Is it reflex? Oh, what would it be reflexive? I think it would be symmetry, right? Because if x relates to y relating to x would be the same logic. Okay. And then the corollary is, of course, the reason why we did that. If x is path connected, and we have 2 points in space, then the fundamental group, if I anchor it at x naught, it's the same group. Whoops. As taking it from the other anchor point. Okay. We have an improved definition for simply connected. So a space X is said to be simply connected if it is a path connected space and if the fundamental group is the trivial group. For some point in space, and hence for all points in the space.
Is that lots of equal?
And then here's the convention I used earlier. So we often
That's more.
express the fact that the fundamental group is the trivial group by simply writing that P1 XX naught is 0. Okay.
Okay, so draw just a circle. So not a sphere, just a.
Well, you want to do
flat circle.
S1 for integers?
Yeah, so.
Okay. This now is S1. So what that means is it's only the boundary points. So don't think of this as like closing some sort of a region. So your set is just those boundary points around here. So now, say I want to choose an anchor somewhere in this set. So maybe I anchor it down here at X naught. Yeah. So what different kinds of loops can we make here? And a loop, of course, it's got to start at X naught and then it's got to end at X naught.
Oh, there's one possible loop so we can intersect on yourself.
Well, so loops are allowed to cross over themselves. So the only restriction we're really saying is that it has to begin and end here, which is pretty loose. So we could go around just a full time, right? So that's a simple loop. So that's one way we can do that.
So you just go a little bit and then go back.
Yeah. So you could go hard way. And then be like, nope, never mind, and then reverse back, and then you're back on X naught. And what you can do is, since we're allowed to cross over, what about the times I want to maybe go around twice before stopping?
Right.
Yeah. And here says I have to stop with only going around twice. And so any number of times that I decide to loop around, and every single time I'm getting a type of path that is not homotopically equivalent to these other ones. And so this is going to correspond. Actually, so we'll prove this, the fundamental group, it's this whole thing. I mean, there's some not fun hardware that has to happen to be rigorous about it, but we can smile and wave and say, well, it looks like it's going to be integers.
Right. What? Does direction matter?
Well, even if it did, if it was positive integers, we would just cite the fact that integers are isomorphic to positive integers.
That's true.
Yeah. Yeah, so I think if you wanted to say positive integers, and then from here say.
But then, wait.
All the
But then
natural,
what about
all
all
the
the-
natural numbers starting at 0.
What about all the times that you don't do a full loop?
Right. He wants to include. Victor
Yeah.
wants to include 0.
Which is why I don't think we should do
But that's
positive
so
integers,
zero.
because you could just stay and that would be 0. So I'm pretty sure we can just cut to the integers. Yeah. Yeah, actually, and then some fun ones too. Well, while we're at it, let's
That's
do
just zero. Okay. So weird.
the fundamental groups that you can get. So now, if I make some sort of a
Donut.
funny thing here, yeah. Ooh, exciting, right? So now if I have some sort of anchor point, say I anchor down here. Okay, so the different kinds of paths we can have are
Now we're doing
So is it still 2D or
nope, 3 dimensions. This is existing in R3.
It's a donut.
anything donuts here?
So think about, I mean, obviously, if I want to just wrap around the contour like this, that's a way I could do it. So that's a type of path. And pretty much any other path that's going to be going like that is So even if I stretched it out and I traveled along here before looping back around, it's gonna be essentially the same thing. I could deform it back onto that idea.
Can you pass it to the other side of the loop and then just go like.
Well, what you can do is, in the same way that going around the circle, topologically, you want to think of this as basically kind of a circle embedded into here.
Yeah.
And so we can loop around multiple times, like a coil,
Oh yeah.
and then have the coil go all the way, around as many times as we want until it gets back to the starting point. And the number of coils we can have is arbitrary, so that's already, we have integers there. And what we've been doing is we've making paths along that surface. We haven't gone inside of our donut. And so even inside of the donut that's just stretched around, if we look at the center point, if we think of,
So you can go in the middle?
yeah, we can go in within the center. So now I can create like this closed path loop that will come to here. And then who's to say? So then all of these other paths I can create. And now I can rotate multiple times around this direction in the circle. So these donuts is kind of like two topological circles happening simultaneously. And so and we call a torus and we define it by it's literally, yes, the product of these two topological spaces. And so the fundamental group here of T, and some call it T1 specifically, but I'm gonna just do this. It's gonna be the same thing as, well, in the same way that this is integers cross integers.
Cool.
So,
Oh, I just once.
well, basically like all coordinate points x, y, such that x and y are integers. So like 4, 7.
Oh, well, okay.
Yeah. Fun, there's some fun goofy stuff here. Okay. Let's take a look at some of these. Yeah, let's prove these because these are good. There's a figure 8 torus that I don't know how to draw. So I figured I'd just look it up later and think about it. Okay, so
Right, with two holes, right?
yeah,
Those are with two holes.
let's see, what time is it? Okay, yeah, let's do this one. So in a simply connected space X, any two paths having the same initial and final points are path homotopy. So it's pretty straightforward. If I'm gonna have alpha and beta be paths from x naught to x1, then the product of alpha with the reverse of beta is going to be defined. And is a loop on x based at x naught. And then since x is simply connected, then this loop is path topic. Path, or this loop is path of a topic to the constant loop. It's not. For we have that I can take the class of alpha times reverse beta times theta, which is going to give me the identity, which returns basically onto the point itself in the path beta, which means that alpha is beta. And if two equivalence classes are the same P, then that means they're in the same path homotopy class. Okay, so let's define.
Just to verify, simply connected means there's no holes in the space, is that right?
Yeah.
Okay.
I'm gonna take x naught to y naught be a continuous map. So this is saying I want to take specifically the point x naught in x to the point y naught in y through h. So we define some map H star be the fundamental group x naught to the fundamental group that you get in y, or to y naught, by the equation H star of some class is going to be the class of H composed with F. So then this map, H star, is called the homomorphism. Homomorphism induced by H relative to the base point x naught. So let's see. I'll state this theorem. The proof is pretty straightforward. If H takes a point in x naught in x to a point y naught in y, and if K takes a point y naught in y to a point z naught in z, and if they're continuous, then the composition of K and H under this definition star should be just K star composed with H star. It's kind of a transitive idea. And if I takes x naught to basically the same very point, this is the identity map. Then the induced homomorphism I star is the identity homomorphism. I'm not really sure why this was categorized as a theorem, because it's kind of just a lemma, since all of the proof is definitional. So by definition, we're going to show that if I take K composed with H star, so the induced homomorphism on this, then if I have the class F, that spits out the equivalence class K of H, which is this, of F path. And then if I decide to do the other way first, so then K star composed with H star, then if I now put the class through this, then all I gotta do is just compose it first. This is really just K of H of this. So K star of H star of the F. And then we can do H star first, which by definition is just going to be H composed with F. And then again, more by definition, this is just K composed with its input, which is H composed with F. And since composition is associative, K of H of F is the same as K of H of F. And then similarly, we can show that the identity homomorphism, if I put in some class, is just going to be I composed with F, and since that's identity, then so knowledge to that one. And then we'll do one more. If H is taking a point x naught and x to a point y naught and y, and this is a homeomorphism. So isomorphism was algebraic structure preserving map. Homeomorphism is going to say topology preserving map. So it's the same idea of x with y. Then the induced homomorphism is an isomorphism of the two fundamental groups with each other. So we'll first define a k to take point y and then go backwards to point in x. And this will be the inverse of h. Then, if I take the induced homomorphism k star and compose it with the induced homomorphism h star, then that is going to be k of h star from the previous lemma or theorem, which in his case, because we defined it to be inverse, this is now the identity homomorphism, where I is the identity map of xx naught. Additionally, if I take the induced homomorphism of H composed with the induced homomorphism K, then I have H composed with K, and then that induced homomorphism again by the previous lemma. And we're gonna have some other identity. So we'll call it J star, where J is the identity map of y naught. So we have an identity map for going back to the x naught point, the point in y as well. And then we say since both the induced identity homomorphisms I star and J star are the identity homomorphisms of the groups P1 x naught, P1 y naught, respectively, then K, the induced homomorphism on K we define is the inverse of the induced homomorphism on H, which is sufficient. we have 5 minutes, and there was one really cool thing I saw about covering spaces. So I'll just show it real quick. It's a way to cover the circle using the real numbers. Actually, not even the reals. You don't need all the reals. You can just do it with integers. So I'm going to define a map P. So think about if I have, actually I'll do real numbers, yeah. So I'm gonna make a collection. I should first define my map. So the map takes P, or that takes the real numbers onto the sphere in one, given by P of x is equal to the point cosine 2 pi x sine 2 pi x. This is a what we call a covering map. This is going to be the most regular math we do in a little while. So Vn, we can take these collections of open sets. So the first one we could use n minus a quarter to n plus a fourth. And what that's going to look like is an R, right? I take, so if this is 0, 1, 2, minus 1, minus 2, then the open set V0, Vn, right, is going to be minus a fourth plus a fourth. So it'll be like, and then V1 will be V2, minus 1, minus 2. And what all this happens is all of that collapses onto through P on the unit circle. While we're looking at what do all of these open into these neighborhoods are all going to collapse onto this, right? And that's that, So we're claiming that the inverse image of a neighborhood with a point over here is going to have some collection of disjoint open sets in the E spaces. This would be considered E to B, and so R to S prime. So yeah, it's kind of like this. And then so on, to make it a covering map, we just need to find, are there other collections of these disjoint open sets from a neighborhood over here? And yeah, we can. So we can take all of the positive x values and all of the negative x values we could get through doing n plus a fourth to n plus 3/4. And that's going to, through P, give us the other side. So this open interval on this left side. So then the inverse image of this from P is going to be the collection of every single open interval in R that look like this. And then now if I want the positives, I'm going to take n plus half, and through P, that's going to give me this upper, the positive y values here. And then lastly, of course, the negatives, which is n minus 1/2 to n. From P that collapses onto this part. So we can cover all of the S1 with collections of disjoint open sets in the other set that they're coming from to P.
So I have two questions. One is, don't we only need two of those to call it covering map?
Yes. Well, it's more like you need to have
Oh,
the union of all of them to do all of them.
okay,
Where's the definition?
that's the endpoints, but I guess that makes sense.
Yeah, so if P E to B is continuous, then every single point that is in here needs to have a neighborhood that's evenly covered by the map P. Where being evenly covered is that if you take the inverse image of that open set in B. So in this case, the open sets of the circle, then you can have disjoint open sets in the set that you're coming from, in this case R, that if you were to map those over, it's going to be open in S1. And they're so yes, it is overcounting in their slices. Yeah. Okay.
Pretty cool there.
Yeah. So the spring break's gonna happen, but I'm gonna keep moving forward to the fundamental group of the circle, and then that means we'll return for fundamental theorem of algebra for the topological perspective.
All right. Thank you. Thanks, guys. Good job.